Hello, my name is Ivan Taylor, and I'm from Policy Dynamics Incorporated in Kitchener, Ontario, Canada. And this is the second half of a presentation that Suraj Kool and I gave to the students of Vanier College in Montreal, Quebec on March 21st to 2023 for their Science Week. The title of this presentation is the United Nations Sustainable Development Goals and System Dynamics. And it's based on work that Suraj and myself and Tak Ono and Bunmi Falabetta have done over the past few years. We built a model to analyze the Sustainable Development Goals for any country in the world. And I'm going to show you today how it was applied to Canada. But first, I want to talk a little bit about how system dynamics works and how we build system dynamics models. So I'm going to provide a little description of a small model of the population of Montreal and the population of the province of Quebec. So we use a software package called VenSim, which VenSim Personal Learning Edition, which you can download for free from the vensim.com website. And we can use this for any personal or learning activities for free. Now, the first thing I'll start with is a stock of the population of Montreal. And then I'll introduce a flow into this population of the growth in the population of Montreal. And then I'll introduce another variable, which is the initial population of Montreal. And I'll introduce another variable called the growth rate in the population of Montreal. And now I'm going to connect these parameters together. So I'm going to connect the initial population to the population, and I'll connect the population to the growth in population and the growth rate to the growth in population. So now I'll put in some formulas. So the first formula I'll put in is I'll specify the initial population of Montreal as in the stock of the population of Montreal, and I'll make the units people. And then I will specify the growth in the population of Montreal as the population in Montreal times the growth rate in the population. And that will be in people per year. Okay, so now we want to estimate the population of Montreal and the growth rate in the population of Montreal. So to do that, I use Excel to minimize the error between data and the model. So here I have data on the population of Montreal and the growth in the population of Montreal between 1950 and 2022. So then I'm going to build a model that is basically the same as the VenSim model, but in Excel. So the first thing I'm going to do is I'm going to add the initial population of Montreal by going here. And then I'm going to have the growth rate in the population, which is the population times the growth rate. And then I'm going to have the population in 1951 as the population in 1950 plus the growth in the population. And then I'm going to cut and paste this down here. Now, what I'm trying to do is I'm trying to get a good match between the data and the model. So here is the actual data on the population of Montreal in blue, and I want to get this pink line in the estimate of the population to match the current population or the past population. So what I do is I have to estimate the growth rate. And I do that by using what's called a lookup table in Vensim, where each year we look up the growth rate because it changes over time. So just taking a look at the growth rate in Montreal, here we see the growth in Montreal has varied quite a bit over the years. So we want to get a match between the data in this column in the growth and this column in the growth, and a match in the estimate of the population and the actual population. So I calculate the growth rate by using a lookup table as shown here. And the lookup table basically uses a methodology called linear interpolation to look up the values in the various years between 1950 and 2022. So now I have the first few years specified. So I'm going to copy and paste this down for the next 70 years. And now I can look at the match between the data. Now, though I should mention that I calculated the proper values for this table to give a good match with the data. And I did that using a statistical technique. But let me just show you the match. And you can see that we get a really good match here between the actual population in blue and the estimate of the population in pink. And we can look here and we can see the match between the actual Montreal growth and the estimated Montreal growth. And we see that we get a fairly good match between the data, the actual data and the estimates. Okay, so now let's go back to Vensim. And first of all, we will specify the initial population. So we'll go back to the Excel model and we will go back to the sheet, and we'll copy the actual population into this formula, and we will remove the commas, and we'll call this people, units of people. And now we have the initial population in the formula. And now we're going to calculate the growth rate. And I have already introduced the table of the growth in Montreal. So here is the table that I've introduced. And I'm going to have another variable called time. And I'm going to now build a function where we look up on the table the growth rate for every year in the simulation. So here we go and we estimate the estimated growth rate as a function of time. Okay, so now we can run this model. And because Vensim is an easy program to work with, we can use it to look into the future. So let's look into the future of the population of Montreal. And we see here that if Montreal continues to grow at its current rate, it could be around 20 million people by the year 2020, 2200. So that's many years into the future. But I also have built a model of the population of Quebec province. So here is the model of Quebec province. And I have the data here and the estimates here and the rate of growth here. And when you look at the match between the model and the data, you see a good match in the Quebec population and a good match in the growth of the population over the years. So I have built this in VenSim as well. So if I go here to this, there's the model for the provincial population. And if I look at the provincial population, I can see that the growth rate in the provincial population is shown here over the next 100 years or 200 years. So now I'm going to show you an interesting result of this model, which shows you some contradictions in this work. So I'm going to estimate the number of people. This is the population of Quebec province outside of Montreal. And so then I'm going to show the population of Montreal, which is the estimated, which is the population of Montreal and the estimated population of the province. And I'm going to calculate now the population outside of Montreal, and you'll see the contradiction that occurs. So here we have the population in the province minus the population in Montreal, and the population in the province should include the population in Montreal. And when we run this, we see that the population outside of Montreal drops considerably over the years. And so this might be a little contradictory. You would, if you, for example, run this model out further. So I built another model of the population of Quebec and Montreal, and this time I used a different methodology. I used the growth of Montreal, a growth of the Quebec province in these cells. And then I said the fraction of the growth of the province that went to Montreal. And that is shown in this graph, and I have a lookup table for this value as well. So here we have the population growth of Montreal as a function of the growth of the province. So, and you can look at the graphs again, and we can see that that the population of the Quebec province is looking very good in the model, and the growth in the province is looking good, and the Montreal population is looking good, and the growth in the population is looking good. So now we'll go to the VenSim model, and I'll show you now the population of the revised model in in VenSim, and we have a revised population of Montreal, a revised growth rate, and we have the fraction of provincial growth that moves to Montreal, and we have the estimated growth of the province. So this is a lookup table here, where we look up the estimated Montreal growth fraction as a function of the population who moved to Quebec. And if we go now to this page, we can now look at another view of the situation where we have now an idea of the revised Montreal population and another variable called the revised population of Quebec province outside Montreal. And if we now calculate this as the population of Montreal, no, we calculate this as the revised population of Montreal and the estimate of the population of Quebec, and we get a new calculation here of the estimated provincial population minus the revised Montreal population. And if we run this now, we get, I think, a more realistic view of the population of the province outside of Montreal. And if you look at the graphs together, you see this picture, which I think shows that the growth of the population will continue to grow as opposed to declining. And if you look at the picture here, you can see that the population of Montreal is now going to be shown in this graph here, and you can see that it's going to be lower than the province of Quebec, which is shown in this graph here. Okay, so that's a little example of system dynamics modeling and showing that you need to look at the system rather than just the individual parts of the system. So we had the growth of Montreal and the growth of Quebec independent, but to look at the picture more realistically, we had to combine the model into a systems model which showed the relationship between the population of the province and the population of the city. Okay, so let's go back to my presentation and let's look at the system, the model that we built, the system dynamics model we built for the Sustainable Development Goals. And recall that the United Nations defined 17 Sustainable Development Goals, and they have a 2030 agenda to reach sustainable development that was adopted in 2015 by all UN members. Now we have a number of issues with this system of goals, is that there's no clear understanding of the causal interactions between the SDGs, and that the SDGs are lagging indicators, which means they're estimating things that happened in the past, and they cannot be used effectively to forecast into the future. So recall these are the 17 SDGs. And so we wanted do a few things. We wanted to establish the interconnections between the SDGs using the system dynamics approach. We wanted to develop a simulation to assess future projections for informed decision-making, prioritizing, and planning. And we wanted to evaluate the simulation for emergent behavior and novel insights. So the methodology was that we found the network diagram that was developed by LeBlanc in 2015, and we established the polarities between the links, and then we translated this network and the polarities into a stock and flow model, calibrated the model using data, and then applied the optimization to the model to get results into the future. So as we recall, this is the network diagram developed by LeBlanc in 2015, where the big circles represent the goals and the small circles represent the sub-goals, and the sub-goals are connected to the other goals. And so this is a larger picture of the same thing, and you can see the names of each of the goals here and the connections in the numbers of the sub-goals. Here is a picture of the polarities, and in this case, we have this idea that a change in one variable could cause a positive change or a negative change in another variable. So for example, in this case, we have goal number 2 has a positive impact on goal number 1. That is, an increase in goal number 2, which is 0 hunger, will cause an increase in goal number 1, which is 0, which is no poverty. And then an increase in goal number 2 would have a decrease in goal number 12. So, and an increase in goal number, a good decrease in goal number 2 would have an increase in goal number 12. So this is the polarities, we call them polarities between the model, and it shows the structure of the model we built. So here's here's a picture of the way the model works with stocks and flows. So we have each of the scores of the SDGs is a stock, and then we have a flow of the progression towards a target, and we have a target here that changes over time. So basically, over time, this goal will try to achieve this target, and then we have this idea of a progression between the score and the initial value. So if the current value is higher than the initial value, that means that there's been progress in this SDG, which will lead to a positive influence in the other SDGs that's connected to it. So here is the results for Canada. You can see that we have data from 2017 to 2022, and we have a picture of how the model tracked the data over that period. And then we extrapolated through using the system dynamics model into the future till 2028. And this extrapolation is not a linear extrapolation like in statistics. It's based on physics and calculus. So you can see that there's a strong curves in these future projections. And here we see the projections for the SDGs 10 to 17. And notice this light, this turquoise line here shows a very low score for Canada in SDG 13, which is climate action. So Canada is scoring very poorly in that SDG. So here are the projections. So you see the values in 2017, the values in 2022, and the projections into the future. And notice here that clean, affordable, and clean energy is also getting a low score of 32 in the future. Here is the projections for this 10 to 17, and we see climate action was declining from 66 to 30 and down to 13 in 2028, according to our model. So we wanted to improve the results for Canada. And the way we decided to do that was by improving the score for the worst performing SDG. And in this case, it's climate action. So we wanted to invest extra effort into Canada's effort to improve the scores of the SDGs, and particularly climate action. So here's the effort that we estimated to be the best way to allocate our effort to get the best values for the minimum score SDG. So we would estimate that 46% of our effort would go towards climate action, and 25% of our effort would go towards affordable and clean energy, and then 20% of our effort would go to SDG 15, life on land. And here's the results when we maximize the minimum score by applying this effort. And you can see here that SDG 7 has now started to improve. It was declining before, and SDG 13 has risen quite considerably. So climate action is being helped greatly by this extra effort. And here's the results. So you can see that by working with the minimum scores and applying this effort, we can actually improve almost all of the other SDGs. Notice two small problems, that good health and well-being declines a little bit from the status quo situation, and gender equality declines a little bit from the status quo projection. But many of the others improve considerably. So affordable and clean energy increases to 64 from a projected value of 32, and climate action increases to 89 from a no change, or the previous estimate of 13. And here is the results of the minimum score, and you see here that the minimum score without any extra effort was shown to be declining, which is climate action. And then with effort to improve the minimum score, we can improve climate action. However, at some point, the affordable and clean energy becomes the minimum score. So that becomes now a new value for the minimum that needs to be acted on. So in this work we did, we found that for Canada, 11 SDGs showed a decreasing trend in our projections into the future. And SDG 13, climate action, was the poorest performing SDG. And so we developed a methodology to improve the minimum, to optimally improve the minimum SDG score. And when we did that, we would suggest that we allocate 46% of our effort to SDG 13, climate action, 25% of our effort to affordable and clean energy, and 20% of our effort to life on land. And in this case, we would find that 5 of our SDGs still have a decreasing trend. However, SDG 3 and SDG 5 will decrease slightly more than previously. So there are trade-offs that will occur when we try to increase this minimum score. Some limitations to this work is that we only have data till from 2017, and so every year they produce a new SDG report, and the model would have to be recalibrated every year and may produce different results. However, that might not be a problem because these policies are developed by the government of the day, and generally governments work on an annual basis. So possibly every year, the government of the day could change the direction of their policies to react to the situation that's happening with the SDGs on an annual basis. Another limitation of this work is that the government of the day must determine the actual policy of changes and programs. So this idea of effort is an abstract idea, and it assumes that each of the SDGs will have the same response to this equal amounts of effort. They're basically equally easy to change, which is a limitation to the model, and we want to look at the future work to examine what if the SDGs had different different challenges in trying to change them. So as I said, future work would be looking at differing effort required to change the SDGs. So some SDGs may be more challenging than others, and assess different optimization goals, like we looked at the optimization of minimizing the minimums, maximizing the minimum score. We might want to, for example, maximize the average score or the median score. And then we want to apply it to many more countries. We've shown this model to Ireland, and we've shown it to some Latin American countries, and we're going to show this to South Africa and Zimbabwe at their conference, System Dynamics conference in November. And then we want to demonstrate this to policymakers to help prioritize the effort to improve the quality of life for a country's citizens. Here are some references that we used to build this model. The Sustainable Development Goals website is shown here, and LeBlanc's 2015 network is shown here, and also we have the Sustainable Development Reports shown here, and they are produced every year, as I said. Thank you for listening, and if you have any questions, we can take them now. And if you have any interest in looking at this model in any more detail, feel free to contact us at these email addresses.